Okay. So last time we talked about KL divergence and the total variation distance, or so-called statistical distance between two distributions. And we'll continue sort of studying maybe the relationship between these two quantities and also some applications in today's lecture. Just to sort of recap, we said that KL divergence is defined as maybe the excess amount you would pay if you kind of encoded according to the wrong distribution Q when the true distribution was P. It's a way of measuring kind of the difference or distance between two distributions, although it's not necessarily symmetric. We saw that it's non-negative, has a chain rule, and we also saw this other notion of distance between two distributions, which is the total variation distance or statistical distance, which we also claimed is, well, I mean, not just claimed, but proved the statement that if I just want to look at sort of a one sample distinguisher between two distributions and just sort of classify, then the best probability for this test of distinguishing between the two distributions, or the difference in expectations of this function f of x, is upper bounded by the total variation distance. And moreover, there's nothing special about the interval 0 to 1. So we could have any bound b, and here we would have b over 2 or b times the total variation distance. So okay. One thing which is good to check, I didn't mention this last time, but check that this is tight. In particular, there exists such an f which can do this. I'm not saying anything about how easy such a test is to compute or anything, but if you know everything about the distribution, I claim that you can find this f. And as a hint, look at the next slide, but okay. So that's a rough recap from last time. Yeah, stop me at any point if you want me to go over something again, if you have any questions. We were sort of halfway through proving Pinsker's inequality. Let me remind you what it is. It says that the KL divergence is always an upper bound on the square of the total variation distance, or L1 distance. They're just off by a factor of 2. And I mean, the precise constant there is this 2 times ln2, because we defined KL divergence with log base 2, and so on. So it depends a little bit on how on your normalization. And we said we proved this in 2 steps. We did the first step, and I'll remind you what that step was. It's just to kind of just collected all points x where p of x was larger than q of x. So when you're calculating the total variation distance, you have this absolute value of p of x minus q of x. These are all the points where the absolute value is not needed. P of x is bigger than q of x, or is at least as large. And I left as an exercise to say that if you now think of a sort of 2-point distribution, or a distribution of support size 2, where you get 1 with some probability, 0 with some probability. These probabilities are determined by kind of just bundling together everything in A. So that's why I'm calling this distribution P sub A and Q sub A. Then the claim was that the L1 distance, or total variation distance, between P sub A and Q sub A is the same as that between P and Q. And the KL divergence can only decrease, so it doesn't increase when I consider P sub A and Q sub A. So in particular, if I can prove this inequality for this distribution P sub A and Q sub, like distributions P, A, and QA, then this will imply the inequality for the original distribution, because the left-hand side can only go down, the right-hand side doesn't change. So, okay. And we prove that the KL divergence can only go down using the chain rule for KL divergence. Everyone okay with that much? And now let's get to the part which we needed to prove, which was the fact that when you have a distribution with support size 2, Pinsker's inequality holds. So let's just prove it in general for 2 distributions P and Q. let's say, which achieve the value 1 with probability p, q0 with 1 minus p, or q and 1 minus q. The L1 distance is just 2 times p minus q in absolute value. And the KL divergence is this quantity. And we want to show that it's greater than equal to 1 over 2 ln2 times the L1 distance. So you just plug in the calculation from the previous line, you get this. So what we need to do is prove this inequality written in red. And I mean, this is just direct calculation. If you know what strong convexity is, you can sort of see that this looks something like strong convexity. But even without doing that, we can just, the strong convexity just says that your function, I mean, the function is convex and it's kind of lower bounded by some sort of quadratic function. And then you do see a quadratic function appearing there. But without getting into that precise definition, we can also just prove it just by computing derivatives. So fix P and think of what happens when you vary Q in this inequality, which is just think of the difference of the two sides as a function of Q. And we'll just calculate the derivative of it and show that it looks like the picture on the right, which means that it's minimized at P, the minimum value is 0. And the fact that f of q is greater than equal to 0 is precisely what we want to prove. That should suffice for our inequality. So we just need to check that indeed the minimum value is 0. So, and it's just by direct computation of the derivative. Let me just write it down. So one thing is the derivative of ln, or the log to base e, is nice to compute. The derivative of ln x is 1 over x. The derivative of log base 2 is sort of harder. So it's easier to just kind of maybe change to log base e by dividing by ln2. So yeah, log base 2 of x is just ln x divided by ln2. So we'll just divide the first two terms by ln2, take it out common. The third one already has an ln2 built into it, and now take the derivatives. Okay, and yeah, it's something you can check. I don't necessarily need to do this in detail, but it will be. Yeah, I'm just sort of writing the terms, doing the derivative in my head. But in case you want me to spell out the details, let me know. Or in case I make a mistake, also let me know. Everybody okay with that? Any disagreements? Right. Assuming this computation is correct, I think so. I mean, the thing to notice is that this term is always greater than equal to 0. For all q, and sort of q times 1 minus q is less than equal to 1/4, or the other way is 1 over q times 1 minus q is greater than 4. And so the derivative in particular is, excuse me, is negative when q is less than p, and is positive when q is greater than p. So the function is decreasing when q is less than p, increasing when q is equal, so q is greater than p, and you can check that it goes to infinity on the extremes. So the graph looks like this. Also, when P is equal to Q, the function is 0 just because you are looking at the KL divergence of P with itself. The two distributions are identical. So yeah, that's just a direct computation to see that the function is minimized at P when it's 0. Okay. Any questions? Okay, before we go to applications of this, let me mention one more property which I forgot to mention last time, which is the joint convexity of KL divergence, in the sense that it's convex in P and Q, but it's also convex in kind of the tuple P and Q together. So if you think of a distribution, like pair of distributions P1, Q1, and a pair of distributions P2, Q2, and now you consider a convex combination which is 1/3 P1 plus 2/3 P2 and 1/3 Q1 plus 2/3 Q2. So convex combinations of two distributions is also a distribution. And so if you compute the KL divergence at this convex combination of the points P1, Q1 and P2, Q2, versus if you compute it at the individual extremes, the function behaves like a convex function. So it's the value at the midpoint is less than equal to the average of the two values. And this is a useful property. You can, of course, you can check that it sort of implies convexity in individually in P and Q. You can just either take Q1 equals Q2 or P1 equals P2. But let's prove the stronger version. Okay. And we'll sort of half prove it, but let's just calculate what's on the left. Let's say sort of all distributions are for X. Everything has to be for the same random variable because that's how KL divergence is defined. And as usual, we can sum over all values and okay, this is just writing out the definition of the KL divergence on the left. Now, I'll sort of cheat and give you the main step as an exercise, but it's using kind of idea we have done many times. So as an exercise, I'll ask you to prove the following inequality. If you have A1, A2, B1, B2, which are non-negative, you can even assume they are all positive just to make things easier. But okay, let's say for this one. Then A1 plus A2 log is greater than equal to A1 times sometimes called the log sum inequality. It's not a very subtle name, but yeah, it's it's the same kind of applications of Jensen's that we have done multiple times. It's a good exercise to try it out. Once you have that, it's kind of done. So I just apply this inequality with these things as being labeled A1, A2. V1 and V2. And once I plug that in, I get okay, and common factors just cancel out. So what you're left with is just okay. Yeah, the key step, of course, I left as an exercise, so I'll let you do that. Any questions?
By the way, the inequality should be reversed in the exercise.
Oh, sorry. Yeah, you're right. Thank you. Okay, now let's talk about some applications, and the rest of the lecture will be applications of Pinsker's inequality. I'll do a couple. So let's talk about the sort of scenario we were referring to last time, that you want to maybe distinguish two distributions using multiple samples, and you want to somehow relate it to the statistical distance or L1 distance, or and then presumably KL divergence, since we are claiming this is an application of KL divergence. So formally speaking, let's say we have two distributions. One is, let's say, a fair coin, or 0 or 1. You can think of 0 or 1 as kind of tails or heads or tails, whatever you like. So yeah, two values, you can name them whichever way you like. So one is a fair coin. It comes up, let's say, heads with probability half, tails with probability half. The other is a slightly biased coin. Let's say it comes up heads with probability half plus epsilon, tails with probability half minus epsilon. And the goal is to distinguish these two so I have one of these two coins. You don't know which one. And I toss this coin multiple times independently, and I give you the outcomes of my coin tosses. And let's say you're interested in designing an algorithm or a tester which looks at the outcomes that I gave you and does whatever computation it wants on these samples, and then tries to guess whether the coin I had was a fair one or a biased one. Okay. This is sort of a toy version of a more general setup called hypothesis testing, where you have some assumption about how your data looks. Maybe let's think of P as what would be called a null hypothesis, Q as what would be called sort of one of the hypotheses that you want to test, that okay, there is some bias in the coin or not. And you're observing presumably independent samples, and then you do whatever computation you want. And most of the time with information theory, we are interested in how much information do you need to make your decision, which in this case corresponds to how many outcomes or how many times do you need to toss the coin. I'm not necessarily bothered about sort of how efficiently do you make your decision by looking at this data. You can do whatever you want. You can do an NP-hard computation on this n 0 ones, do whatever you want. By the way, based on what we know about sufficient statistics, what is the computation you should do, or what should you look at?
Can you just look at the likelihood of all the sequences?
Likelihood under which distribution?
Just trying to calculate two likelihood under both
Yeah, so you can
distributions.
look at the likelihood of the two. Uh, and actually, because of the way the problem is set up, the likelihood will only depend on how many zeros and how many ones are there. So in particular, it suffices to look at summation xi, which is, as we saw, is a sufficient statistic to distinguish. This was an exercise last week. So, I mean, sufficient summation xi is still a number between 1 and n, or this likelihood is some sort of collection of probabilities, and you can still do all kinds of computation. If the third bit of this number and the fifth bit of this number are the same, then you do something. Who knows what test you're going to run? I don't know. But for now, we are not bothered about that. We're just saying how many samples do you need to see. Okay. Is the setup clear? Okay. Now let's try to phrase it in the language of statistical distance or one sample distinguishers, let's say. So let's say the tester has 90% accuracy. I've drawn the cartoon of this tester again here, which means that when you give it samples from P, it says that the outcome is from P with 90% accuracy. When you give it samples from Q, it says the outcome is from Q with 90% accuracy. So what can I say about the two probabilities that I've written down here? Can you give me a lower bound on each of these probabilities? It's not very subtle. The answer is already written on the slide. You just have to tell it to me again. So, no? Maybe it's too simple. Or
0.9 for
90%?
Yeah, just that. So, I mean, I'm just saying the same thing which I said earlier in English now in terms of probabilities. So when I sample from P, the test tells me that the outcome is from P with probability 90%. And when I sample from Q, the test tells me the outcome is from Q, or the guesses that the outcome is from Q with probability 90%. Yeah, it's just restating what I already said a minute ago. Okay. And T is a function which is 0 or 1. So now we can write it in terms of this sort of one sample distinguisher kind of language by saying you just think of T as a function on x1 to xn. And we know that by assumption, it's a 90% accurate distinguisher, which means that the expectation of T when I sample from, it will be 0 with probability at least 0.9. And so it will be 1 with probability at most 0.1. So that means that this expectation will be less than equal to 1/10. And this expectation is just the same as the probability we wrote. So this will be at least 9/10. And so that the difference of the two expectations will be at least 4/5 or 8/10 in absolute value. So now it looks like very much a statement of the type we saw for statistical distance. Just to remind you of the statement. If you have any function which takes samples and looks at on one sample, it sort of the expectations differ by at most whatever is the statistical distance between the two distributions, P and Q. And now we just kind of changed the definition of what it means to be a sample. A sample is, for this test, is n independent tosses of the coin. So that's just what we will call one sample. And now, and again, there is nothing special about 90% accuracy. You can see that if it was anything bigger than 50%, you would get some sort of constant lower bound on the right hand side. So yeah, 90% is just makes us feel better than when I say 51%. Okay, so what this tells me is that the total variation distance between p to the n and q to the n, where p to the n is shorthand for the product distribution for n samples, each drawn independently from p. And this is at least 4/5 because it's an upper bound on whatever is the difference in expectations for a one sample distinguisher. So in particular, this must be at least 4/5. You can also think of the L1 distance. Now, before we go any further with this, so we are trying to calculate, so this is a necessary condition for no matter what tester you have, the L1 distance between p to the n and q to the n, or the half of the L1 distance must be at least 4/5. Okay. And when n is 1, what does it look like? Let's just at least check that some lower bound on n is required. So when n is equal to 1, so remember the two coins were just sort of 0 or 1 with probability either half or something very close to half. So when you calculate this distance, it will be 2 epsilon. Or if you calculate half of that, that will be half of 2 epsilon, which is epsilon. So it starts out at epsilon, and we are trying to understand if we take n copies of this distribution or take a product distribution, how does it grow? How does the L1 distance or the total variation distance grow with this operation? And we are trying to say, can we upper bound how much it grows, so that we say that, well, you should take n at least 100 or a billion or whatever, so that it grows sufficiently to 4/5. And the problem is that it's a little difficult to analyze the statistical distance of p to the n and q to the n, even if p and q were very simple, because even though p and q had support size 2, p to the n and q to the n have support size 2 to the n. There are like a sequence of coin tosses, and at least from the definition of the L1 distance, it seems like we will have to write down all 2 to the n probabilities, calculate the differences in the two cases, and that seems like a lot of work and not always easy to analyze. What is easy to analyze, and as I kind of alluded to last time, that a lot of information theoretic quantities work well because they have chain rules. So they are usually easier to analyze on product distributions. So what is easy to analyze is the KL divergence. And then we'll use Pinsker's inequality, etc. But let's start with the KL divergence, and let's see how this grows as I change n. Any questions so far? Okay. So let's calculate the KL divergence. And remember, and now I'm kind of writing it out explicitly as samples x1 to xn and the distribution for x1 to xn, just to sort of be clear on the notation. But this is just the same as the KL divergence of p to the n and q to the n. It's just each sample is sampled independently from p. Okay. Now, what is the first term? So this is just the behavior of the first sample. The first sample is sampled from x1 is kind of either sampled from p or sampled from q. So this is nothing but the same as the KL divergence of p and q. Okay, what about the second term? So remember, this is actually a shorthand. This is a shorthand for the value of x1 sampled from, in this case, p again, times the KL divergence between x2 such that x1 is equal to whatever value we got. So it's a shorthand for this quantity. Can you tell me what this quantity is?
Should be just the same as the first. It's the IID.
It's the same as the first because the samples are independent, both in the case of P and in the case of Q. So it's important that both of these distributions have independent samples. So it doesn't matter what the value of the first coin toss was, I still get the KL divergence of P and Q. And the same is true as I kind of keep going along. All of these terms are just... So all I get is something very simple, which is n times the KL divergence of... So the KL divergence of P to the n and Q to the n is very, very simple to calculate. Well, we're not done yet. We need to actually understand this number D, P, and Q, which is actually not too bad. So let's forget the n and let's write out this number. So P was half and half. So I mean, yeah, it's not very deep, but it's worth doing this calculation at least once. I just added the logs and multiplied the terms. And then I can just use the fact that 1 plus x is less than equal to e to the x, or ln of 1 plus x is less than equal to x. So I get that this is less than equal to, sorry. Okay, I did all of that, but I'll just say this is less than equal to some constant times epsilon square. Doesn't matter. If you calculated Q and P, if you flip this, this will also be some other constant potentially times epsilon square n, but the epsilon square is the interesting thing to remember. N we already derived earlier. All right, so that's just the bound that we get on the KL divergence. And now we can kind of finish the proof just by sort of using the bounds we derived on both sides. So we know that the L1 distance has to be at least, oh, sorry, I forgot a square. It has to be at least, thought I got 8/5 square, some constant. And then here we got that the KL divergence is at most n times epsilon square. Let me write down the exact numbers. Okay, and so yeah, you can do the calculation with it, but you'll get that n must be larger than some other constant c prime times 1 over epsilon square. Okay, so it's a simple fact, but it's used a lot of the time that just to kind of distinguish two coins where the biases differ by epsilon. The number of tosses you need is 1 over epsilon square. It need not be always true. It's true when the kind of coins are very close to half. The biases may be half and half plus epsilon. And you'll see a homework problem about other regimes. But any upper bounds, any suggestions? If you can suggest a test, or if you can say, so maybe there was a likelihood test suggested, any guesses on how many samples do we need for that test to work? So as I said, I mean, this is a toy problem, but it's quite commonly used whenever you have two hypotheses which are slightly different and you want to understand how much data you need. And surprisingly, often you can actually just reduce it to the question of two coins with a slightly interesting definition of coins, maybe. I claim that the upper bound is also 1 over epsilon square. And let's say C double prime sort of is as an exercise, I'll ask you to say that check that using Chernoff bounds, you should be able to distinguish these two coin tosses. I mean, yeah, if the sample was coming from P, what's the chance that more than half plus epsilon of them are ones? You can calculate an upper bound on this probability using Chernoff bounds. And so your test can be just something like, if you're seeing too many ones, more than half plus epsilon or more than half plus epsilon over 2, and then we'll see where to exactly locate this. But should be easy to say that there is some threshold you can say, and above that threshold, you're very unlikely to go when you're coming from P, but you're very, very likely to go when the samples are coming from Q. And the probability of deviating by epsilon over 10, let's say, from that threshold will be 2 to the minus epsilon square times n. So you can check using Chernoff bounds. I mean, we'll be able to kind of say more precise things about the number, but at least some constant times epsilon 1 over epsilon square, you should be able to just check from whatever form of Chernoff bound you apply. Any questions? So yeah, I'll leave that as an exercise to check.
Can I ask a question?
Yeah, please.
I don't understand this upper bound stuff because it seems like the more samples you get, the better, right? So why is your upper bound on the number of samples?
Good. So yeah, so upper bound, yeah, I should specify the task more correctly. So upper bound for 90% accuracy, let's say. So the more samples you get, the more your distinguishing probability can get close to 1. And we said that if you want to hope for 90% accuracy, you need at least 1 over epsilon square samples, some constant times epsilon square, 1 over epsilon square samples. And I claim that you can also achieve 90% accuracy with maybe some other constant times 1 over epsilon square samples. Okay, so the upper bound is for achieving 90% accuracy. And yeah, your accuracy can get arbitrarily close to 1 as you get more and more samples. Okay. But this much suffices for if we are just setting the bar at 90%. Does that clarify the question?
Yeah, I think so. Thanks.
Other questions? Okay. Now let's see an application to a slightly more involved setting. As you'll see, it's again sort of the same calculation with maybe a little care and some slightly more carefully defined random variables. But let me first introduce, not give the full bound, but I'll do some sort of toy version. But let me introduce the problems called, this is a class of problems called bandit problems. So the name bandit comes from, I guess, slot machines in a casino or something where you have different arms and different machines. You can pull one of them, you see what the outcome is. So each machine has some reward at any given time, and then maybe you play for a while. A casino, maybe not for too long, but as a sort of at every point in time, all of the machines have different rewards, and which I will denote by kind of x11 to xk1. These are the rewards at time 1. Then x12 to xk2. These are rewards at time 2, and so on. And at time t, you make a choice. You kind of pull the arm c sub t, which denotes your choice at time t, and you get to see the reward of that machine at time t. You don't get to see the rewards for the machines where you didn't pull the arm. So, okay. And the question is, how well can you do? How much reward can you accumulate? In general, not that I'm sort of particularly keen on casinos, but in some sense, these are good model problems for capturing a lot of learning settings where you have maybe multiple algorithms, or you're trying to learn from different hypotheses about data. But the point is, you only get to observe as a result of some action you take, like maybe in routing problems, or sort of if you're driving somewhere, you get to see the traffic on the road you drive on. Maybe with Google Maps, you get to see the traffic on other roads as well, but at least it used to be an example of partial information. But there can be many other, like if you're doing some sort of experiments in biology, maybe you will get to see the result of the experiment you do, but not necessarily all the others, and so on. So it's a common model for various kinds of partial information settings. And the quantity, which, again, this is just one way of measuring how well you do. So it's so ignore the first part for now. Actually, just focus on this term, which is the last term here. This is the reward you actually get. At time t, you made the choice c sub t. This is your actual reward. And this sort of denotes the best arm in hindsight. If you had to play on one machine in hindsight, why one? Yeah, it's a bit arbitrary in the sense that what about the best sequence of n machines? That's a bit unfair, because in some sense that's too much hindsight, and then you can show that there is no way to compete against that strong an objective, where you kind of had no information versus sort of you can choose arbitrarily good decisions with the benefit of arbitrary amount of hindsight. But you can sort of replace this one arm by multiple kind of ways of measuring some kind of low complexity strategies, that maybe you switch between 2 arms, maybe you switch between 10 arms, maybe you switch, but it's sort of a tree structure. So there are many different ways of modeling what it means to use the hindsight, but only in some sort of low complexity way. And yeah, this is one of the simplest. We just pick the best. And so this difference between what you could have done and what you ended up doing is called regret. And the goal is to sort of minimize your regret over all the sequence of choices you make. Now, there are a few things to clarify about what do your choices depend on, whether things are deterministic, who chooses the rewards and how, and so on. And these are sort of defined very different bandit settings. The one we are looking at is, it's sort of the lower bound will give holds for a couple of settings, but a common one is just adversarial setting where the adversary gets to choose excuse me, the rewards based on what you're doing, except that, the adversary doesn't look at your choice at time t before choosing the rewards for time t. Otherwise, the adversary can just kind of set your reward always to 0 and you have no hope. So this also, will in fact give something which applies to a weaker model where, so we are going to give lower bounds. So lower bounds, it's nicer if they apply even to weaker models. And in particular, there's also a model where each arm has some fixed distribution. You just don't know what it is. So this is more like the machines in a casino, which hopefully nobody is tampering with them while you are playing them, but they presumably could have different settings before. And you just don't know which one is good, which one is bad, which one to play on. And there, in some sense, picking one machine also makes a little sense. And this could be random. It doesn't have to, the rewards could be random. They don't have to be deterministic. Presumably, any slot machine has some randomness in it, maybe pseudo randomness, whatever. And you could also use, and your choices only depend on what you see. So at the step 1, you have to just kind of walk up to the machine and pull an arm. You don't have any information. At step 2, you know what reward you got and which machine you used. You can use all that information to decide what to use next. At step 3, you could look at your history, sort of which are the machines you used at step 1 and 2, what are the rewards you got, and then use this as a basis of your choice for step 3, and so on. So your choice depends on the history. So the C1 to CT is like, it's not a sequence which is fixed ahead of time. It's kind of develops as you see more of the X's. And these are the things which make the application kind of require a little bit of care. You have to define things carefully, but at the end, it kind of just boils down to tossing coins. Okay, is the model okay? Any questions about the model before we proceed? Okay. The lower bound I'll sort of allude to, but not necessarily prove this full thing, is something which is very similar to the hidden or coins example that we saw. So there is one arm which is special, let's say arm I. This has a coin which is biased. So you get a reward of 1 with probability half plus epsilon, 0 with probability half minus epsilon. All the other arms are just fair coins. You get 1 or 0 with probability half each. And this is a lower bound example due to our Cesabianchi, Freund, and Shapire from 2002. And there is a nice long form survey / book by Bubak and Cesabianchi, which gives a good exposition of bandit problem literature. So these are good places to take a look if you want to read about these problems in more detail. But the bound roughly shows that the regret is greater than equal to epsilon n times some quantity which we'll just say is sort of very close to 1 minus 1 over k, assuming n is not too large or epsilon is sufficiently small, pick whichever way you want. And in particular, if you choose epsilon correctly, which is about some constant times capital K over n, then the regret comes out to be about square root n times capital K, which is the number of arms. This is known to be almost tight for this problem. So what do I mean by almost tight? There are algorithms which give square root n times k times log k, I think. Yeah. And although, I mean, I'm sort of, there is a little bit of contest about log k, like various of these algorithms actually bound something which is called pseudo regret. And the lower bound also kind of gives the lower bound of pseudo regret. Pseudo regret has a tight upper bound of square root n times k. This log k is only needed when you go between regret and pseudo regret. And then there is some contest about whether that's really needed or not. So, well, not without getting into that, kind of gives at least a fairly tight lower bound. What I'll do is sort of a kind of toy version of this, which captures essentially all the ideas, which has a bound of this form. And one way to think about this bound is kind of, and which is the sort of way we will emphasize. If you were to just guess which is the arm which is the right one, which is the arm which has this special reward, if you just guessed it correctly, then you would presumably do epsilon better than if you didn't know anything. And if you were to just guess at random, you would have a probability of 1 minus 1 over k of being wrong. So this is the probability of being wrong if you just guessed the correct arm at random, tried to do that. Or if you, out of your n choices, you tried to guess things at random, about n times 1 minus 1 over k would be wrong choices. And so this bound sort of says that not only is it true that you can't kind of find this arm, you make the same number of mistakes over n choices as if you were just picking things at random. And then we'll make this more concrete in a toy example, but we'll sort of show this for a simpler case. Okay. Any questions? Okay, so let's look at the baby bandit problem, the baby version of the problem. It's also more fun to think about baby bandits. So it's a bandit problem where, let's say we have two arms, and let's say I have two coins in my left and right hands, one in each. And unknown to you, one of them is a biased coin, the other is a fair coin. And we don't know which is which. Let's say I kind of picked a random variable capital H, which either came out to left or right, and then I placed the biased coin in my left hand or right hand accordingly. Okay. And H was, let's say, left or right with probability half. And now I'm doing the same thing. I'm kind of tossing both coins, which are these X's. You make a choice at time t, which is C sub t, which is either left or right, and then you get to see the outcome of the coin in whichever hand you choose, which I'm going to call Z sub t. So Z sub t kind of denotes what you actually see at time t. So it's X L comma T if you chose to see the left hand, and it's X R comma T if you chose to see the right hand. Okay. And let's say, yeah, you ask me to see whichever coin. And if it comes up heads, you sort of get $1. And now let's say the question is, how many dollars can you make this way? Okay. Is the setup okay? It's just the bandit problem with two arms. Okay. But we'll kind of illustrate, I mean, essentially all the things that come up in the proof with K arms sort of also show up here. Okay. First question, if you knew which is the sort of hand which has the biased coin, how many dollars can you make?
If you knew which hand has the,
Yeah.
you make N dollars?
No, it's still a random coin. So, and you only get $1 if it comes up heads, right? So it could happen that nothing. So it's still a probabilistic event, right? It's
I'm actually confused about the process. The
good. That
problem
was- So yeah, so the process is you get $1. If whatever hand you chose to see has a heads in it. Okay, so I'm tossing these coins. X's are being chosen at random. You choose to see one of them, okay, without knowing the outcomes, of course. So at time t, I kind of tossed the coins and I held them in my hands. And now you ask me to either see the left hand or the right hand, and I open it and show it to you. And if it's one, you get $1. If it's heads, you get $1. If it's tails, you don't. Does that make sense? The model?
Madur, on
Yeah.
the top right corner, shouldn't that be PL is like 1/2 plus epsilon and then 1/2 minus epsilon?
Yeah. Okay. So I was using shorthand. So when I say half plus epsilon, I actually mean it's 1 with probability half plus epsilon and 0 with probability half minus epsilon. And similarly, this is sort of 1 with probability half and 0 with probability half and so on. Okay. So there are actually two coins. Each of them have two outcomes, 0 or 1. And I can place the coins in two ways. So there are lots of things going on even in this baby version of the problem. First, I kind of have the biased coin in my left hand or right hand. Then I toss both of them. You choose to see either my left hand or my right hand. And then whichever hand you choose to see could have come up heads or tails. Okay. And then if you chose to see a hand which did come up heads, then you get $1. It's not so easy to make $1. I'm giving away a lot of money. But okay, does that make sense now?
Both of your hands have two coins, right? Both of your hands
Both
have
of
coins.
my hands have one coin each.
One of them is the biased one, and you
One of them
decide.
is the pair one. You just don't know which one is which.
Okay, got it. And the biased one prefers one of the either head or tails.
Yeah, it prefers
by-
the outcome which gives you more rewards. So it prefers heads, and you get more dollars for heads. You get
Okay.
$1 when it comes up heads. Okay. So yeah, now can you tell me what's the best you can do if you knew which hand has the biased coin?
Is it one?
Yeah,
plus-
Sorry.
Is it 1/2 plus epsilon times n?
Yeah, good. So it's a in expectation, it's a half plus epsilon times n. If you knew the bias coin, you would just always pick that hand, and in expectation, you have a probability of getting half plus epsilon times $n. There is a subtle issue that the best of the two hands in terms of what the expectation is going to be need not be the expectation of the best of the two hands. So you could have tossed them 20 times and then picked the best out of the actual coin tosses, not with the probabilities. It's a subtle issue I'll ignore, but this is actually the difference between regret and pseudo regret, but I'll kind of ignore it for now. Okay. It's the best according to outcomes or best according to some sort of expectations. But yeah, let's not worry too much about it. Let's say in expectation, you would have made half plus epsilon times $n. If you didn't know, how much can you make? Again, in expectation.
half times n by 2.
Okay. I claim you can do a little better.
Is it half times?
randomly, and then you choose plus epsilon over 2.
Sorry, can you say that again?
Well, epsilon n over 2 plus.
Yeah.
Just choosing.
So you can do a little better. I mean, you can say that with probability half, I'll choose the left hand. With probability half, I'll choose the right hand. And so in expectation, I will make half plus epsilon over 2 times $n. you don't even have to use probability. You could say the first time I pick the left hand, second time right hand, then left, then right, then left, then right, and keep going. Right? So, and in fact, this is true in general for this setting, that you actually don't need to use randomness, which is what we will use in proving the bound. You can sort of, if you can do something with randomness, you can just kind of pick in different sequences, or you can just kind of fix some value of your randomness and it will still give you the same kind of bounds. Okay, good. So that's, so the whole game is this sort of extra gain of epsilon n over 2. And the question is how close, like there is a difference of about epsilon n over 2 between the best and what you can do without knowing. And the question is how close we can get. And we'll show that if n is small, you can't do that, or unless n is smaller, like unless n is bigger than 1 over epsilon square, you can't really quite do much better. And yeah, you might as well just pick between the two hands randomly. Okay, so now let's try to formalize this. So I claim that the expected loss, and again, I'm cheating a little bit, but the expected loss is the epsilon times the number of times that you picked the wrong hand. Why is this? Because this is either let's say the correct hand was the left one. At time t, your loss could have been what you would have done if you knew that the left hand was the right one to pick, or the left hand was the correct one to pick, minus what you actually picked. And either you actually picked the left hand, in which case your loss was 0, or you picked, oh, sorry, why am I writing y? Or you pick the wrong hand, in which case your loss was epsilon. The difference in expectations between XLT and XRT is epsilon. So every time you pick the wrong hand, you lose epsilon, and otherwise you lose 0. And so now we just need to understand how many times do you pick the wrong hand. And I can write this as in terms of this hidden variable, or this variable which corresponds to which is the hand which has the bias coin. It's either the left hand or the right hand. And then I can ask what is the number of times you picked the right hand when the biased coin was actually in the left one, and the other way around. Notice that these two probabilities need not be equal. It depends on what your strategy is. Your strategy could be anything. Maybe you always pick the left hand. That's your strategy. So then the first probability or the first term will be 0. The second term will be what I'll need to calculate. So it depends on your strategy. We can't just ignore this, but it's not too bad to kind of understand the two. So first of all, I kind of assumed that each of these terms is just half. I either pick the biased coin in one hand or the other with equal probability. So that is easy. And now I'll write it both in terms of picking the left hand. So I'll say n minus expected number of times so the number of times you made the kind of wrong choice is n minus the number of times you made the right choice, or the correct choice rather than right choice. And I'll leave the other term as such. And now it's starting to look a little bit like this one sample distinguisher, or some sort of difference in expectations under two distributions. There is one distribution in which the biased coin is in the left hand. You're saying, what is the number of times I picked the left hand under this distribution? Versus there is the other distribution when the biased coin is in the right hand. How many times did I pick the left hand under this distribution? Okay. So it's starting to look a little bit like the expressions that we calculated for statistical distance. And we can formalize that by sort of saying so remember, Z1 to Zn denoted the data that you actually saw. And if I fix your strategy, whatever strategy you are going to sort of adopt, then the number of times you pick the left hand is a function purely of the data that you saw. Right? There is nothing else. It's a function. So it's, I mean, as I said it's also a function of the choices you made and the data that you saw based on those choices. But your choices that you made at time 1 or at time 2 were the function of a data that you saw at time 1. So at time 1, you made a choice which is just fixed in your strategy. At time 2, you made a choice which depended on Z1. And at time 3, you made a choice which depended on Z1 and Z2, which also happened to determine all the choices you made before, and so on. So I claim that the number of times that you choose the left hand is a function purely of the data that you saw. Once I kind of fix your strategy in terms of what you're going to do with that data, but that we always fix, right? I mean, we fix T, which is whatever is the code of the algorithm when it was looking at the samples. So where f is just a function which calculates number of times and this is the key step that somehow, although it kind of sounds complicated, that sort of someone reveals a reward, you look at that, then you decide to see the next one, then based on that, you decide to see the third one. At least when we write it in terms of the Z1 to Zn, it's just purely a function of what we saw. Z1 to Zn could be a complicated random variable because remember, Z2 kind of depends on what is the choice you made at time 2, which tells me which X that you saw, and so on. So it could be a little involved, but at least writing it as a function, it's sort of easy to understand. Just that the only thing it depends on is the values of Z1 to Zn. Is this point okay? This is kind of the key step even in this K-arm bandit problem. I mean, once you set up the right function and the right Z1, the Z1 to Zn are the same functions, you have to look at a couple of functions, but that's about it. And this function is something which takes value between 0 and n. It's the number of times you pick the left hand. So it's the difference in the function is upper bounded, or the number of wrong choices is lower bounded by half times n minus n over 2 times the I'll write whatever is the distribution you get for Z1 to Zn when the biased hand was the left one, minus whatever is the distribution you get for Z1 to Zn when the biased hand was the right one. This is not necessarily a product distribution. It's a slightly funky distribution because it also depends on your choices and so on. So, but it's still the L1 distance. Okay. And if we can show that the second term is small, then we would have shown that the number of wrong choices is about n over 2, which is what we were claiming anyway. Any questions about this part?
In the first step itself, where number of counting of CT is equal to R, could you say that this is just independent of H is equal to L, or?
No, it could depend on your strategy, right? So you can say that if I see more ones in one of the hands, like I will kind of try to alternate between them for 20 tosses, and then after that I'll pick whatever I get wherever I see more ones in the first 20 tosses. Okay. So, and it's more likely that you will see more ones in the biased hand in the first 20 tosses. So maybe after the 21st toss, you are just going to pick that. In general, you will kind of bias the one towards the one where you've seen more heads, or you will, and this is in general in bandit problems, there is this sort of exploration versus exploitation. So for some time, you're just trying to figure out where you are seeing more rewards. And then you will, for a while, then you kind of, where you see more rewards, you pull that arm a little more. And sort of these kind of phases happen. And so what is your decision after exploration, or what do you choose to exploit will depend on H. So it's not always true that, I mean, it depends on your strategy, and your strategy could be anything. So we can't really assume that in general. Okay. In general, in fact, like most strategies will have some dependence on H, which is how they will try to compete against the best arm. Okay. Other questions? All right. So it comes down to now computing the KL divergence between these two distributions. By Pinsker's inequality, again, we want to upper bound the L1 distance. We'll use KL divergence. Try to use the chain rule, although the random variable is more complicated. Let's see what the chain rule gives us. Okay. So it's, I mean, the calculations are not that difficult. You just have to maybe understand the definitions of various random variables involved in these bandit problems. It takes a little bit to sort of get used to the setup. But otherwise, it's not a difficult calculation. Okay, so we'll use chain rule, and we'll just say that this is equal to now, the first term is, so first of all, Z1, is it the coin from my left hand or the coin from my right hand? I don't know, you tell me, right? So it's it depends on what your choice is in terms of, depends on C1. So and depending on whether C1 was trying to see, let's say, the left hand, then it would be the KL divergence of the half plus epsilon, half minus epsilon distribution versus the half-half distribution. Or it could be the KL divergence of the half-half distribution, half minus, so half plus epsilon, half minus epsilon distribution. So you could be asking to see kind of the left hand or the right hand, but then it's not too bad either way. It just tells me which term gets placed first in the KL divergence, okay? Which of the distributions. Both of these are less than equal to some constant times epsilon square. One of them we computed already. You can check for the other one. So they're both about epsilon square. And the same is true at every step of this calculation. So no matter what Z1 came out to, you will look at Z1, you will look at your strategy very carefully, then you will tell me what C2 is. And now C2 will either ask to look at the coin in the left hand or the right hand, in which case I will calculate one of the two KL divergences that I wrote down. So again, it's either this one or this one. Both of them are less than equal to some constant times epsilon square. So you will get a bound which the whole thing is less than equal to n times some constant times epsilon square. Even though the distribution is very complicated, it's just that each term is one of these two things, and we have a bound on both of them. And that's about it. I mean, once you can say this, you just sort of plug them back in the computation of the number of wrong choices. Okay, great. So there is a question that do you need to assume that there is no randomness in the strategy? So not necessarily, although the way I'm describing it, I'm kind of using that assumption. I'm saying that maybe you look at your strategy very carefully and then you pick one of these two terms. You can see in one of two ways that you don't really need randomness. One is to say, well, you pick one of these two terms, but now you pick, maybe instead of saying you pick either the first KL divergence or you get the second KL divergence, you will get maybe the first KL divergence with probability 1/3 or the second one with probability 2/3, and both of them are bounded by epsilon square, so it doesn't matter. So your strategy in either case will, you will get some term which is upper bounded by epsilon square. Another way of saying it is that we can look at our expected loss, and this is an expectation over my randomness and also your randomness. And if I fix your randomness, I'm proving that no matter what values you choose for all the random coins that you were using in making your decisions, for each of, like, fix whatever random choices you are going to make to some deterministic ones, right? So you kind of looked at some outcomes and on the side you toss some random coins, fix all those coins. Now you have a deterministic strategy, and I'm proving a lower bound for every possible deterministic strategy, so it will also prove a lower bound for your random strategy. We can discuss this more if needed, but some kind of describing as if you didn't need randomness, and that is the case. Although in principle you could have randomness, the same bound would hold. So once you kind of plug this back in, you get that the expectation or the expected loss is equal to, remember, epsilon times the number of wrong choices. We said that the number of wrong choices is n over 2 times, or rather, let me write it in the form of k bound. So it's half minus half times the L1 surface is greater than equal to the L1 distance between PL and PR. And this is greater than equal to epsilon n times half minus half times some constant times the KL divergence, or the square root of the KL divergence, which is epsilon square n. And so at least as long as n is small, you're going to make roughly the same number of mistakes as you would have made if you were just picking things at random. Okay? Or the number of wrong choices would be about n over 2. A slightly more careful version of this argument will also give you the more general bound for K arms. You can take a look at the surveys if you're interested. I'll be happy to discuss them in my office hours if you want. Okay. And I'll stop here for today. Next time I'll talk a little more about kind of continuous random variables and entropy, KL divergence, etc. for those. Fine. Stop here. Any questions?
Hey, again about the setup. So at the start of the experiment, you pick one of the hands where the biased coin is going, right? Left or right. And then you do, and then the seeker, the player asks, show me. Okay, okay.
Yeah, so I never changed the hand. Like it always stays in one of the hands. That is like, otherwise, even the best strategy has no hope of competing. If I keep switching my hands, then like there is no single choice of a hand which will win overall also. And that I need to compare against a single hand at the end of the day. So I kind of pick one of the two hands. I don't tell you which one. And then at the end of this, I'm going to tell you that, oh, if you had picked the right hand, you would have always gotten better outcomes.
So it's basically the two-arm bandit problem.
It's the two-arm bandit problem with a very special distribution on the two arms. Yeah, but it's sort of, yeah, I find the K-arm bandit problem has sort of essentially a similar proof, except that the setup becomes already a little more sort of confusing because the Z's and the F that we use becomes a little more complicated. So it's a slightly more involved, but conceptually, this is all there is to it.
All right. Okay.
Madhur, could you comment on the chain? So like when you condition on C1, yeah, so like, can you explain a little bit more about why the right-hand terms have the same upper bound?
Okay, you mean the KL divergence terms?
Yeah.
Okay, so first notice that C1 is not something I'm conditioning on. I'm, as I said earlier, I'm kind of assuming that your strategy is fixed, deterministic. I mean, it still depends on the outcomes of the tosses. So in some sense, I'm conditioning on C1, but C1 is just a deterministic function of Z1. Or sorry, C1 is a deterministic function of nothing. Sorry, C1 is just, you have already a strategy in mind, and your strategy says the first time I'm going to look at the left hand, let's say. So C1 is just dependent on your strategy. Okay. Now, if you are going to look at the left hand as the first step of your strategy, let's say C1 is equal to L. Then what are the two distributions I'm going to look at? The two distributions I'm kind of asking for is the KL divergence of P sub L of X L1 versus P sub R of X L1. What is P sub L and P sub R? P sub L and P sub R are actually distributions on both hands. It's just, they are just telling you where the biased coin went. So you are going to look at my left hand, and I'm calculating the KL divergence between the two cases where my left hand held the biased coin versus my right hand held the biased coin. Okay. And the outcome you are going to look at is the outcome of my left hand. So in this case, the outcome of my left hand is a half plus epsilon, half minus epsilon biased random variable. In this case, because the biased coin went in my right hand, the outcome of my left hand is a half-half biased random variable. Okay. Similarly, if your choice was to look at my right hand, then we will still be calculating PL and PR, but now we would be calculating it for these random variables. And now we are saying, if the biased coin went in my left hand, and when you're trying to look at the outcome of my right hand, what's the distribution on that? It's the fair distribution. And if you're still trying to look at my right hand, but the biased coin was also in the right hand, then it's this distribution. So at least at the first step, depending on the choice of C1, I'm calculating one of these two KL divergences. Both of them are upper bounded by some constant times epsilon square. At the next step, it's basically the same thing. Now I'm conditioning on some value of Z1. Conditioning on the value of Z1 does not change where the bias coin is. In some sense, does not change PL or PR. PL or PR already have the information about the bias coin built into them. Okay. So if you condition PL on the value of Z1, PL is a product distribution. It sort of already has the information built in about where the coin went. PR is also a product distribution. So conditioning on the value of the bias coin does not change PL. It changes what Z is. It changes what hand are you going to look at, because your strategy has some choice for C2, which potentially depends on the value of Z1. But it's again going to be either L or R, C2. And in both cases, I'm going to again look at one of these two decadal divergences. And so in each case, I'm going to get an expression which is upper bounded by some constant times epsilon square. Does that make sense? It's slightly subtle, right? So yeah, it's
Thank you.
Other questions?
Yeah, I'm wondering if you could go over again why you can write the C T's as a function of the Z T's on the previous slide.
Randomness, or just for a deterministic strategy, why are they function of Z's?
Oh, I thought, okay, so in that step, you're already just saying you're looking at a deterministic strategy.
Yeah. So I was kind of, the way I described it, I was looking at deterministic strategies. So you could have had randomized strategies, then for every fixing of your randomness, there would be deterministic functions. So what does it mean that you are using randomness? It means that you're looking at your outcomes, and on the side somewhere, you're also tossing some coins. And then you make a decision based on what your random coins told you and what the outcomes were. That's a generic way of using randomness. Okay. So now I'm going to say, toss all your coins ahead of time. Okay. It's equivalent because it's sort of, even if you're going to toss different number of coins based on different outcome, just toss as many as you need. Keep a fixed value.
Yeah.
And now it's a deterministic function of the outcomes. And you need a little argument to say that, and in fact, what I'm saying is that no matter how you tossed your coins, or for every fixing of your random coins, the expected loss would still be large. So in particular, for any randomized strategy where you would be using some sort of distribution over these coins, it would still be large, because for every fixing, it's bad in expectation over what I'm doing. Does that make sense? This point,
Yeah.
you can kind of say more formally if you like, but
it's similar. I guess it's similar to saying like every random strategy is some combination of deterministic strategies, right? It's
true, but I mean, there is a little more sort of here. It's not true in general for the bandit problem, at least in the adversarial setting, where the rewards could be anything based on the actions you took. Then it's not always true. It's true here because of a very special assumption that the rewards are just coming from some distributions, and they never, the adversary, or like when I'm deciding the rewards, I never look at what you did. They're just kind of, I have some distribution. It's either the biased coin in my left or right hand, but that never changes based on what you are doing throughout. In this case, it sort of, you can actually pull out the random which you would have used. And I can show this more formally if you want in office hours, or I can just write it up and show it to you later. But it's not true in general for the kind of most general case of the bandit problem. I should just emphasize that.
Yeah, okay, that makes sense. Thank you.
More questions?
Can I ask about on page 12, how do you go from the second line to the third line?
The second line to the third line. Okay, so this is sort of a rephrasing of what also Max was asking, is that I'm claiming that because my choices are a function of the outcomes that I saw, so the number of times I asked to see the left hand, or I made a choice of L, is just a function of the outcomes that I saw. The outcomes I saw are Z1 to Zn. So the number of times I picked the choice L is a function of Z1 to Zl. That's
Wait, because I thought you pick a hand and then you gotta see the eye, right? Like a time t, you gotta pick first, right?
Yes, but it's a, okay. So it's a subtle inversion of that. So suppose I told you some strings z1 to zn. Let's not think of them as outcomes or anything yet. Let's just think of strings z1 to zn.
Mhm.
This completely determines the choices you would have made. So, I mean, I'm going to, I fixed some string ahead of time, and now I just decided that I'm going to give you this string z1 to zn. So you made a choice. Okay, show me the left hand. And I said the outcome of the left hand is z1. Then you asked, show me the right hand. I said the outcome of the right hand is z2. I fixed this string as the stuff that you are going to see. And my claim is that if I fixed the stuff that you are going to see, then the choices you are going to make are also fixed, because the choices you make are just a function of what you see.
Okay, so you're basically saying there's like a one-to-one map here. So if you know one thing, it's like a bijection, like based on the stuff you pick, it's the z1, the zn you see, it's like equivalent, right? Or
It's not a bijection in the sense that, I mean, the set of your choices might be smaller than the possible outcomes. Your choices could be that I will always see the left hand. And so there is a bijection then, like irrespective of z1 to zn, you will always see the left hand, because that's what your distance strategy is. So
okay,
it's not a bijection, but it's a one-way map. So I'm just saying that if I tell you, if I know all the outcomes that you are going to see, then I know what choices you are going to make. The outcomes determine your choices, not necessarily the other way around. So it's not a two-way map, but it's a one-way map.
Okay, another thing is if you're gonna invoke the inequality to the first line, isn't the f supposed to be like an indicator function? So it only outputs 0 and 1?
No, it works for any function which takes values between 0 and some bounded value b.
Right. Oh, I saw you modified that this
so,
time. Yeah, I got it. Yeah.
I mean, in fact, when we proved it last time, we also stated this. And if you go through the proof, it never uses the fact that the function is an indicator.
Okay, I see.
I mean, the proof we wrote kind of uses that it's between 0 and 1. But if you prove it for between 0 and 1, you can just multiply both sides of the inequality by b and it still works.
Yeah.
If you have a function which is between 0 and b, just divide that function by b and then apply the inequality.
Okay, got it. Thanks. Let me digest this a bit. Thank you.
Sure. Other questions?